Good morning, welcome back. Let's do some equilibrium math. So we did the concepts, we did a review of the concepts, and I secretly set you up for the math. Here's how. Okay, so the very last thing that we did was here. We were thinking about things that stay constant at equilibrium, even though the whole process is super dynamic, right? Constantly in motion, rate forward and rate backwards may all be really fast. But if they're equal, over time, we see this net constant amount of product and reactant. Okay, we can describe that using math, unsurprisingly. And we're gonna, don't worry, we're coming right back here. But I'm showing you how I set you up for this. So KEQ is the equilibrium constant. So anytime you're looking at equilibrium math, you're looking at a KEQ. K because we use K for constant for reasons that may or may not make sense to anyone. And EQ means equilibrium, so this is your equilibrium constant right here. Your KEQ, in its simplest form, is this ratio. It's the amount of product divided by amount of reactant is your KEQ. Doop-a-doop. That's all. There's more. Of course there's more. But in its simplest form, your KEQ is a ratio of product to reactant. KEQs are super helpful because if you know one of these things, try again, if you know two of these things, you can solve for the third, which makes sense. Yeah, okay. It does get a bit more complicated. Off we go. Okay. So we're just gonna look at a super generic chemical expression. What does that even mean? We've got some reactant. Here's your reactants. This is your coefficient, how much of your chemical A is going to react with your coefficient, how much of your chemical B. So, for example, this could be 3 moles of chemical A combined with 2 moles of chemical B to form a reversible chemical reaction. You're going to get a forward rate and a backwards rate. And then here's your products. Let's say 2 moles of chemical C and 14 moles of chemical B. I'm just making up numbers. But these little numbers are coefficients. So A, B, C, and D are coefficients. And your capital letters here are your chemical compounds. This is just totally shorthand. And don't worry, we will do examples also. Chemical compounds. Yeah, so it's a totally generic reaction. Along with it being generic, you may at some point have a reaction that has only one product. If it doesn't have a second product, don't worry about it. In that case, you've only got one product that you're working with. Similarly, if your reaction only has one reactant, don't worry about the other one. There's only one reactant that you're looking at. Sometimes reactions can have like 3 products, in which case do include all 3. This is like a super generic picture as your initial introduction. Okay, we're going to use that to write this ratio. You're going to put your products on top. And here we go. So your products are C and D. You're going to put them in little brackets. This little bracket means how much. So the bracket means concentration. This is a little out of order because we'll do more with concentration on Monday. How to think about concentration is like if you're we often make lemonade in class. There's lemonade day as concentration day. And we're like, some people like really sweet lemonade with tons of like lemonade powder. Some people like way more water than lemonade. Those are all concentrations. How concentrated is the solution? So you could take a ton of powder and just a little bit of water, see if you can dissolve like the powder into the water. That would be really, really high concentration. Or on the other side of the spectrum, if you have a big glass of water and you just put a tiny bit of powder, that's a low concentration of lemonade in your water. We'll do, I almost switched today and Monday because I haven't taught you concentration yet. But this goes with the equilibrium stuff. Yeah. Those brackets, what that bracket means, like what it's saying, is the concentration. It's almost always in the units of capital M. Why that is relevant is that when you see your math is going to say, I'm going to choose actual picture. Your math is going to say maybe I should switch these days. So math says, here's your unit. Actually, here's how we're going to do this. That's your unit. That's the same thing as a capital M. But for now, we're going to say this has the units of moles per liter. So when you find, or let's just do both, or capital M. So when you find your numbers, they are going to have the units of moles per liter or the units of this capital M. We'll do examples, don't worry. Okay, so amount of product, your products here are C and D. So that bracket says amount, concentration of product C times concentration of product D raised to the power of the coefficient. The coefficient becomes the exponent. So these little numbers, the coefficients, become the exponents in your equation. So chemical C, the amount of chemical C raised to the power of its coefficient times the amount of product D raised to the power of its coefficient That's your product sentence. Divided by your reactants. Let's do it. We've got the amount of reactant A raised to its coefficient times the amount of reactant B raised to its coefficient. That's your KEQ. So you've got this ratio, amount of product relative to the amount of reactant ratio. That ratio will stay constant at equilibrium. You've got your amount of product on top, amount, concentration, amount of chemical C raised to its coefficient times the amount of product D raised to its coefficient. All your products go here. If you had 16 products, they would all go there on top. All the products, the amount, the concentration of the product raised to the coefficient in the balanced chemical equation times all the other products. Here we've got two products. If you had 3, you would have 3, etc. So that's your top is your amount of product relative to, here's your ratio, divided by your reactants. Here we have 2 reactants, A and B. Some number of moles of A, some number of moles of B. And your general equation follows the same format. So the amount, the concentration of A raised to the coefficient for A times the amount, concentration of B raised to the power of the coefficient of B. Feel free to pause this and watch it a million times. This we will do more with on Monday. So unfortunately, just kind of buy it for now. And we'll do more to figure out what that means. And in good news, especially since you have this here, Monday's going to be real easy. That's part of why I'm sticking you with the math over the weekend, because you're going to have a few more days of thinking about it. And in some ways, it's not going to get worse than this. I don't know if that's a helpful thing to be thinking about. Because now we have our general equation, now we just plug in numbers and do math. Okay. Let's do it. Okay. Think about math. If you have a big KQ, say 1,000. Okay. What would that mean about the reaction at equilibrium? So let's say you've got a KQ of, and think about what KQ is. So amount of product divided by amount of reactant and your KQ in this case, let's say it's 1,000. Okay. Think about it. Does 1,000 mean 1,000 over 1 or 1 over 1,000? That is your KQ. What do you have more of at equilibrium? Your KQ says you're at equilibrium. Your rate for it is equal to your rate backward. We're saying that in this case your KQ is 1,000. You've got more product. So a big KEQ means more product at equilibrium. Okay. So that would be like if you had your pencil and you were balancing your pencil on your finger, and one side was so heavy that the balance point was over here where 1,000 of your pencil were on the, let's do it over here, 1,000 of your pencil were on the product side, and only 1 of your pencil were on the reactant side. I have no idea if that analogy made sense. In terms of actual chemicals and stuff, at equilibrium, when your rate forward is equal to your rate backwards, a KEQ of 1,000 means that you have 1,000 products, compounds, particles, for every 1 reactant particle. So big KEQs means that you have more products. Let's take it the other way. What if you've got a KEQ that's really small? So again, this is a ratio of amount of product over amount of reactant. And in this case, you've got a tiny, little tiny KEQ. Some, your big number here, that is 1 divided by, I don't even know how many zeros. 1 divided by a whole bunch of zeros. Small KEQs means there's lots of reactant. At equilibrium. Okay. I will do a math question with you. I think I will do your math question in the next video. Stay tuned. That's coming real soon.